In this video, we are going to find positive integers n and k such that n plus 1 all to the power k minus 1 equals n factorial. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. First, we consider any prime factor p of the number n plus 1. Then this prime number p divides n factorial plus 1 from our given equation. But neither 2, 3, 4 all the way up to n, all the numbers except 1 that are less than or equal to n, would divide this expression n factorial plus 1, because all these numbers that I mentioned are factors of n factorial. But now we added this number by 1, so then these numbers will not be a factor anymore. So this means for our prime number p, it must be at least a number that is larger than all the numbers that I mentioned above. So there has to be at least n plus 1. But p divides n plus 1 under our assumption. So this p is just exactly equal to n plus 1. This implies that n plus 1 actually must be a prime number. So now we have the fact that n plus 1 must be a prime number. And then we divide into two cases. The first case would be if n is even. This is actually most of the case, because when n is even, n plus 1 is odd, so we're actually just considering odd primes for n plus 1. Then we write n equals 2m, some natural number m. Then furthermore, if I further say that assuming this m is larger than 2, then I can write n squared as 2mn, because I've assumed that n is 2m, so I rewrite one of the n's into 2m. So we have the product 2mn, and these three numbers supposedly should be distinct, because I assume that m is larger than 2. So the product of these three numbers that are all less than or equal to n should divide n factorial. So that means n squared also divides n factorial. Now from this we know that n squared will also divide this expression, n plus 1 all to the power k minus 1. So we can say therefore n squared divides this expression, and by binomial theorem we can write that as n to the power k plus k choose 1 times n to the power k minus 1 all the way down to just k choose k minus 2 n squared, and then plus k choose k minus 1 times n plus 1 minus 1. So that's by binomial theorem. But for all the terms in the first row, all of these terms are just by definition multiples of n squared. So I only have to consider the final terms, but the plus 1 and the minus 1 also cancels out. So that means n squared actually just divides k choose k minus 1, and that's k times n, which means n has to divide k. Now that's important, because then we can know that k must be quite a large number. At least it has to be equal to n. So I would say, in particular, k has to be larger than n. But this will cause a contradiction, because that means for our n plus 1 all to the power k minus 1, I will say is larger than n to the power k, and that has to be larger than or equal to n to the power n from our result obtained just now. But this is clearly larger than or equal to n factorial. So this means for our given equation, one side must be larger than the other under all of our assumptions. And we've actually assumed that n is even, n equals 2m, and m has to be larger than 2. And of course we know that m plus 1 is a prime number. So that means we're actually considering primes that are at least 7, because from the condition that m is larger than 2, we know that m is at least 3. So n is at least 6, so m plus 1 is at least 7. So what remains is that we have to we have to consider for cases that n plus 1 equals to 5, 3, or 2, the missing primes. So it remains to consider cases n equals 4 because n plus 1 is 5, and so on. So n equals 4, 2, or 1. Now if n equals 4, then 5 to the power k minus 1 equals 4 factorial, and that gives k equals 2. If n equals 2, then 3 to the power k minus 1 equals 2 factorial, and that gives k equals 1. While if n equals 1, finally, 2 to the power k minus 1 equals 1 factorial, and again k equals 1. So altogether, we have 3 solutions: 1, 1, 2, 1, and 4, 2. And this is our final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.